Gravity is the invisible tether that anchors every moon, planet, and star within the vast and silent cosmic expanse. It remains a constant presence in every moment of our lives. No known material can shield an object from the persistent reach of a gravitational field. While lead blocks X-rays and walls stop light, gravity passes through every physical barrier in the universe without losing strength. This provides a stable foundation for everything we observe. Please consider liking the video and subscribing to this channel. The kind of science that carries the mind gently outward. Gravity technically has an infinite range, even if it becomes incredibly weak over massive distances. Every single atom in a human body is exerting a tiny pull on the most distant galaxies in existence. It is a thought that spans the entire cosmos. This force is surprisingly the weakest of the four fundamental interactions known to physics. A small household magnet easily overcomes the gravitational pull of the entire Earth to keep a postcard attached to a fridge. Unlike magnetism or electricity, gravity only attracts and never repels. Because it lacks a repulsive component, it can accumulate over vast distances to build structures as massive as superclusters of galaxies. Mass and energy dictate the strength of this pull by warping the geometry of space. Observations by the Hubble Space Telescope have confirmed that even light follows these invisible curves as it travels across the universe. This is a good companion for science for sleep. The physical presence of any object in the universe creates a persistent pull on everything around it. This effect depends entirely on the amount of matter packed into a space, which scientists define as mass. The more mass an object contains, the more authority it has over the geometry of its surroundings. Every atom contributes to this collective reach. When you think about the objects in your childhood home, can you remember which ones felt the most solid or heavy to pick up? That sense of weight was actually a measurement of the Earth's massive core pulling on the mass of that specific object, while the object itself was pulling back on the Earth with its own tiny gravitational field. The difference in their sizes made the object's contribution nearly impossible to detect without specialized equipment. This is a good companion for the quieter hours. Even a coffee mug or a heavy book on a nightstand exerts a real, measurable gravitational force on the person sitting next to it. Because these everyday items have such little mass compared to a planet, their pull is too weak for our nerves to register. However, in the silent math of the cosmos, that attraction exists and never truly disappears. The strength of this connection changes rapidly as objects move apart from one another. Scientists describe this using the inverse square law, which explains why gravity's grip loosens so quickly with distance. If you were to double your distance from a source of gravity, the pull wouldn't just be cut in half. It would actually drop to 1/4 of its original strength. It is a geometric reality of our three-dimensional world. Imagine a light bulb glowing in the center of a dark room, casting its radiance in every direction. As you move further away, the same amount of light has to spread out over a much larger surface area, becoming thinner and dimmer. Gravity behaves in much the same way, thinning out as it expands into the volume of space. Small changes in distance result in significant changes in force. This explains why the Moon remains caught in our orbit, while much larger planets like Jupiter do not simply pull us away from the Sun. Although Jupiter is vastly more massive than the Earth, it is so far away that its gravitational influence on us is remarkably small. Proximity often matters just as much as size when it comes to the cosmic dance of the planets. The balance of these forces keeps the solar system predictable. Dense objects pack their mass into a very small volume, allowing you to get much closer to their center of gravity. Since the pull is strongest at the center, being able to stand close to a concentrated mass creates a much more intense gravitational experience than standing on a fluffy, spread-out cloud of the same weight. This relationship between density and distance defines the intensity of the pull. In the vacuum of space, this invisible tether is what prevents galaxies from simply flying apart into the void. Each star pulls on its neighbors, and the collective mass of billions of stars creates a gravitational anchor that holds the entire spiral structure together. It is a subtle but unbreakable bond that dictates the motion of everything from dust motes to suns. Science for sleep helps us visualize these silent connections. The center of gravity for any object is the average position of all its mass, often called the center of mass. For a perfect sphere like a marble, this point sits directly in the middle, but for irregular objects like a human being or a jagged asteroid, that point shifts depending on how the weight is distributed. Everything moves as if its entire mass were concentrated at that one single point. When two objects in space interact, they don't just pull on each other from their surfaces. They are effectively reaching out toward each other's centers of mass, trying to close the gap between those two invisible points. This internal focus is what allows astronomers to calculate the orbits of distant moons with such incredible precision. It creates a reliable map of movement across the stars. Even the air we breathe is held against the surface of the Earth by this constant downward tug. Without gravity's relentless pull on every nitrogen and oxygen molecule, our atmosphere would simply drift away into the vacuum of space. We live at the bottom of a deep gravitational ocean, protected by the very force that keeps our feet planted on the ground. This weight of the air is a constant, invisible embrace. Every person also carries their own personal gravitational field wherever they go, tugging slightly on the walls, the floor, and the clouds high above. While we usually only notice gravity when we drop something or climb a hill, we are active participants in this universal attraction every second of our lives. It is the fundamental language of physical existence. We often imagine our world as a perfectly smooth, solid marble spinning through the void. In reality, the Earth is far more irregular, a churning ball of rock and metal with a surface that rises and falls in ways the eye cannot always see. This unevenness means that the pull of gravity is not the same everywhere you go. The planet is a restless work in progress. Because the Earth spins on its axis, it isn't a perfect sphere, but rather an oblate spheroid. Centrifugal force pushes the material at the equator outward, creating a noticeable bulge that makes the planet wider than it is tall. This extra distance from the center of mass means that gravity is actually slightly weaker at the equator than at the north or south poles. Weight is a variable, not a constant. If you were to weigh yourself at the equator and then travel to the high Arctic, you would find that you weigh about 0.5% more at the pole. This isn't because your body has changed, but because you have moved closer to the dense iron core of the planet. Scientists use this knowledge to calibrate sensitive equipment used in physics and engineering. A good companion for the quieter hours. The true shape of the Earth, when accounting for these gravitational differences, is called the geoid. This mathematical model represents what the global ocean surface would look like if it were influenced only by gravity and rotation, without any tides or winds. It reveals a lumpy, potato-like surface where the sea level would naturally sit higher in some places and lower in others. It is a map of the invisible forces beneath us. Deep beneath the crust, the mantle is constantly moving in slow, massive currents of molten rock. These convection cells can pull down on the crust or push it upward, creating subtle variations in the local gravitational field. Where the rock is denser and cooler, the pull of the Earth is slightly stronger than where the rock is hot and less dense. The ground beneath us is rarely still. In parts of Canada, particularly around the Hudson Bay region, researchers have identified a significant gravitational depression. For decades, the pull of gravity there was measured to be lower than in the surrounding areas, a mystery that puzzled geologists until they looked back into the distant past. It turns out the Earth has a very long memory. Have you ever noticed how a heavy footprint in damp sand slowly fills back in once you step away? During the last ice age, a massive ice sheet several miles thick sat directly over North America, its immense weight crushing the crust deep into the mantle. Even though that ice melted thousands of years ago, the ground is still slowly rebounding upward in a process called post-glacial rebound. This temporary displacement of mass is what causes the lower gravity readings in the bay today. The Earth is still recovering from the weight of the ice. NASA and the German Aerospace Center launched a pair of satellites known as GRACE to map these fluctuations with incredible precision. By measuring the tiny changes in distance between the two spacecraft as they pass over different regions, they can detect the movement of water, the melting of glaciers, and even the shifting of tectonic plates. This is the kind of science that carries the mind gently outward. Other anomalies exist in the deep reaches of the Indian Ocean, where a massive gravitational low spans millions of square miles. Here, the sea level is actually lower than the global average because there is less mass beneath the seafloor to pull the water toward it. Scientists believe this might be the ghost of an ancient ocean floor that sank into the mantle millions of years ago. The history of the planet is written in its weight. Large mountain ranges like the Himalayas also create their own gravitational signatures, but the effect is more complex than just having more rock in one place. The thick roots of these mountains actually displace denser mantle material, which can sometimes lead to a lower gravitational pull than a simple surface measurement would suggest. This delicate balance between the crust and the mantle is known as isostasy. Everything is seeking a point of equilibrium. Even the changing of the seasons can cause a measurable shift in the Earth's gravity as massive amounts of water move around the globe. When heavy snow piles up in the northern hemisphere during winter, that concentrated mass subtly alters the local pull of the Earth until the spring thaw arrives. Gravity responds to the arrival of every rainstorm and the drying of every desert. It is a living, breathing record of our environment. These tiny variations are essential for modern life, as they allow us to track the health of our planet from high above. By monitoring the subtle tugs on satellites, researchers can see how much groundwater is being used in hidden aquifers or how fast the Greenland ice sheet is losing its bulk. Gravity acts as a silent witness to the changing state of the world. It provides a clarity that human eyes cannot reach. Looking upward from the surface of our planet, the moon appears as a silent, glowing neighbor, but it is actually locked in a physical embrace with Earth. This connection is maintained by a gravitational tether that stretches across nearly 250,000 miles of space. Because the moon is so massive relative to Earth, it doesn't just circle us. The two bodies act more like a single, dual system moving through the void. The kind of science that carries the mind gently outward. One of the most visible results of this partnership is the way the moon always shows the same face to us. This isn't a coincidence, but the result of a process called tidal locking, where Earth's gravity has spent billions of years acting like a set of brakes. The constant pulling on the moon's mass eventually slowed its rotation until it matched its orbital period exactly. A slow, cosmic synchronization. This gravitational braking works both ways, and the moon is actually returning the favor by very gradually slowing down Earth's own rotation. Millions of years ago, a day on our planet was significantly shorter than 24 hours because the Earth was spinning much faster. As the moon pulls on our oceans and our crust, the resulting friction acts as a drag, adding a few milliseconds to the length of a day every century. Energy is never lost, only moved. While we often say the moon orbits the Earth, they actually both orbit a common point of mass known as the barycenter. Because Earth is so much heavier than the moon, this center of gravity isn't out in space between them, but is located about 3,000 miles from Earth's center. It sits deep beneath the surface of the ground, meaning the Earth actually wobbles slightly as it follows the moon's lead. A hidden center for a grander dance. Can you recall a time you stood by the ocean and watched the water slowly creep up the sand? This rise and fall of the sea is the most direct way we experience the moon's gravity here on the ground. As the moon passes overhead, its pull creates a slight bulge in the Earth's oceans, stretching the water toward it. This doesn't just happen on the side facing the moon, but also on the opposite side of the planet due to centrifugal forces and the way gravity weakens with distance. The world is constantly stretching and compressing. As the Earth rotates beneath these water bulges, any given coastal point will pass through them, creating what we perceive as high tide. It isn't so much that the water is moving toward the shore, but rather that the land is rotating into a deep pocket of water held in place by the moon. The timing of these tides shifts slightly every day because the moon is also moving in its own orbit, changing the angle of its pull. A precision found in the rhythm of the waves. The sun also plays a major role in this tidal choreography, though its massive distance makes its influence weaker than the much smaller moon. When the sun, moon, and Earth all align during a new or full moon, their gravitational forces combine to create especially high and low tides. These are known as spring tides, which have nothing to do with the season and everything to do with the geometric alignment of celestial bodies. A reinforcement of invisible strength. Conversely, when the sun and moon are at right angles to each other from our perspective, their gravitational pulls partially cancel out. This leads to neap tides, where the difference between high and low water is at its smallest. This constant tug-of-war ensures that the global ocean is never truly still, kept in a state of perpetual motion by the heavy objects surrounding us. The kind of science that carries the mind gently outward. This gravitational interaction even affects the solid ground beneath your feet, though in a much more subtle way than the oceans. The Earth's crust actually rises and falls by several inches twice a day as the moon passes by, a phenomenon scientists call terrestrial tides. We don't feel it because the movement is so broad and gradual, but sensitive instruments can track the entire continent breathing upward toward the sky. A heartbeat felt only by the planet itself. Gravity also ensures that the moon is slowly drifting away from us at a rate of about 1.5 inches every year. As the Earth's rotation is slowed by tidal friction, that lost energy is transferred to the moon, pushing it into a slightly higher and wider orbit. In the very distant future, the moon will appear noticeably smaller in the night sky than it does today. A long, slow goodbye across the eons. This outward migration is a direct consequence of the conservation of angular momentum within the Earth-Moon system. If you look at the history of this relationship, the moon was once much closer, and the tides it caused were likely hundreds of feet high, scouring the early continents. The moon we see now is the product of a stabilizing force that has shaped the very environment where life began. Stability born from a constant pull. Within this system, there are regions where the gravitational pull of the Earth and the moon balance out perfectly with the centrifugal force of a smaller object. These are known as the Earth-Moon Lagrange points, and they represent stable pockets where a satellite or a cloud of dust can stay parked without using much fuel. They are the quiet eddies in the gravitational stream of our local space. Natural harbors in a sea of vacuum. The moon's gravity also provides a vital service by stabilizing the tilt of Earth's axis, which keeps our seasons predictable over thousands of years. Without a large moon to act as a gravitational anchor, Earth would likely wobble wildly like a spinning top that is losing its speed. This would lead to extreme climate shifts that could make the planet far less hospitable for complex life. A silent guardian of the global climate. Even the shape of the moon itself is distorted by Earth's much stronger gravitational field, resulting in a slight bulge that points toward us. If the moon were made entirely of liquid, it would be stretched into an even more dramatic egg shape by our planet's pull. This constant stress creates deep moonquakes, which are seismic vibrations caused by the internal grinding of lunar rock under Earth's influence. A bond that is felt deep within the stone. The Sun contains nearly all the matter in our solar system, creating a gravitational well so deep that it dictates the path of every planet, comet, and grain of dust for billions of miles. This massive curvature of space ensures that even the most distant objects, like the frozen bodies in the Oort cloud, remain tethered to our central star. Without this unrelenting grip, the planets would simply drift away into the cold void of interstellar space. A tether made of invisible geometry. The Sun's mass is so great that it accounts for roughly 99% of the total mass in our entire neighborhood. This overwhelming presence creates a gradient of gravitational pull that forces the inner planets to orbit at much higher speeds than the outer gas giants. Mercury must race around the Sun in just 88 days to avoid being pulled into the solar furnace, while distant Neptune takes over a century to complete a single circuit. Balance found in the center of the storm. Jupiter acts as a secondary anchor in this system, possessing more than twice the mass of all the other planets combined. Because of its immense size, Jupiter exerts a gravitational influence so strong that it doesn't actually orbit the center of the Sun, but rather a point just outside the Sun's surface. This shared center of gravity, or barycenter, makes the Sun wobble slightly as the giant planet moves through its long orbit. A heavy hand on the cosmic scale. This planetary giant serves as a gravitational vacuum cleaner for the inner solar system by intercepting dangerous debris from the outer reaches. Its massive gravity can slingshot incoming comets out of the solar system entirely or pull them into its own thick atmosphere, preventing catastrophic impacts on Earth. Many astronomers believe that without Jupiter's protective presence, life on our planet might never have had the millions of years of stability required to evolve. A silent protector in the outer dark. Between the massive pulls of the Sun and the planets, there are specific pockets of stability where gravity and orbital motion cancel each other out. These are the 5 Lagrange points, named after the mathematician who first calculated their existence in the late 18th century. At these unique locations, a small object like a satellite can stay in a fixed position relative to 2 larger bodies with very little effort. quiet harbors in the solar wind. One of these spots, known as L2, sits about 1 million miles away from Earth in the opposite direction of the Sun. This is the current home of the James Webb Space Telescope, which uses the gravitational balance of this point to stay perfectly aligned with Earth while keeping its back to the Sun. By sitting in this gravitational pocket, the telescope can maintain the incredibly cold temperatures needed to peer back into the dawn of the universe. A steady gaze from a fixed vantage. Thinking back to your own experiences with maps or navigation, have you ever found a spot where the wind or the current seemed to disappear entirely? The science of these stable points is a perfect match for bedtime listening. Further out in the solar system, Jupiter's gravity has trapped 2 large groups of asteroids at its own Lagrange points, leading them in a permanent dance ahead of and behind the planet. These are known as the Trojan asteroids, and they have been held in these gravitational traps for billions of years. They serve as a pristine fossil record of the early solar system, pinned in place by the same forces that keep the planets in line. History frozen in a gravitational embrace. The asteroid belt itself exists largely because of Jupiter's disruptive gravitational influence, which prevented the rocky debris between Mars and Jupiter from ever coalescing into a full-sized planet. The giant planet's gravity kept the material moving too fast and at too many different angles for it to clump together effectively. Instead of one large world, we are left with millions of fragments that continue to collide and grind against one another. A landscape defined by what could not be. Saturn's rings are another masterpiece of gravitational interaction, where tidal forces prevent the icy particles from ever forming a moon. If these particles tried to bunch up, Saturn's gravity would pull them back apart, keeping them spread out in the thin, beautiful sheets we see through telescopes. The rings are essentially a collection of tiny satellites that are being constantly teased and herded by the gravity of Saturn's larger moons. Orchestrated motion on a grand scale. Even the orbits of the planets themselves are not perfectly circular, but are slightly stretched into ellipses by the competing pulls of their neighbors. This gravitational tug-of-war is known as planetary perturbation, and it causes the orbits to shift and wobble over vast stretches of time. It was the mathematical study of these tiny wobbles in the orbit of Uranus that allowed astronomers to predict the existence and location of Neptune before it was ever seen. The map is written in the movement. Gravity also acts as a long-distance messenger, allowing us to detect planets around other stars by watching how those stars move. When a star appears to jitter back and forth, it is often because the gravity of an unseen planet is pulling on it. This radial velocity method has revealed thousands of alien worlds, proving that the gravitational web we see in our solar system is a universal blueprint, a signature left across the light years. The Kuiper Belt, a vast region of icy objects beyond Neptune, is also shaped by the gravitational reach of the giant planets. Neptune's gravity has pushed many of these objects into resonant orbits, where they complete exactly 2 laps around the Sun for every 3 laps Neptune takes. This mathematical harmony is a direct result of billions of years of gravitational sculpting in the outer reaches of our neighborhood. A rhythm dictated by the heavy and the far. The sun's gravity even warps the path of light as it passes nearby, a phenomenon first confirmed during a solar eclipse in 1919. This provided the first hard evidence that gravity is not just a force between objects, but a fundamental curving of space itself. It showed that even the weightless particles of light must follow the contours of the gravitational landscape created by massive stars. A bend in the very fabric of reality. As we look toward the edge of the solar system, the sun's influence eventually fades into the gravitational background noise of the Milky Way galaxy. The Voyager spacecraft, launched in the 1970s, are currently feeling this transition as they move into interstellar space. They are the first human-made objects to begin the long journey away from our star's immediate gravitational family, heading toward the deeper currents of the galaxy. Small messengers on a long, outbound tide. For centuries, the world followed the idea that gravity was a simple tug between objects, like an invisible rope pulling them together. But around 100 years ago, a new understanding emerged that changed everything we thought we knew about the universe. This shift moved us away from seeing gravity as a force and toward seeing it as the very shape of the world around us. A change in how we see the invisible. Imagine a large, flat sheet of heavy fabric stretched out until it is perfectly level and tight. If you place a small glass marble on the sheet, it sits still. But if you then place a heavy metal sphere in the center, the fabric sinks and curves under its weight. Any smaller marbles you roll across the sheet will naturally spiral toward that central dip, not because they are being pulled by a string, but because the floor they are walking on has changed its shape. This is the geometry of existence. According to Albert Einstein's general theory of relativity, space and time are not separate, empty stages where events happen. They are woven together into a single, flexible fabric called spacetime that responds to the presence of matter. Everything with mass creates a curve in this fabric, and we experience those curves as the pull of gravity. The ground itself is bending. In this new model, Earth doesn't stay in orbit because the sun is grabbing onto it with a force. Instead, the sun's massive weight has created such a deep indentation in spacetime that the Earth is simply following the straightest possible path through a curved environment. It is like a cyclist riding around the banked curve of a velodrome, held in place by the geometry of the track. A path set by the shape of the dark. Because it is the fabric of space itself that is curved, even things without any weight at all must follow those bends. This includes light, which we usually think of as traveling in perfectly straight lines through the void. When a beam of light passes near a massive object like a galaxy or a star, it hits a curve in spacetime and swerves, changing its direction. The starlight finds a new way home. This effect is known as gravitational lensing, and it allows astronomers to use the universe's most massive objects as giant magnifying glasses. When a cluster of galaxies sits between us and a much more distant light source, the gravity of the cluster bends the distant light around it. This can make the faraway object appear brighter, distorted, or even visible in several places at once. A cosmic mirror made of pure mass. The confirmation of this idea came from observations made by the Royal Astronomical Society during a total solar eclipse in 1919. They watched as starlight passing near the sun shifted its position exactly as predicted by the math of relativity. It was the first time humanity saw proof that the sun wasn't just a heavy ball of gas, but a heavy weight pressing down on the geometry of the cosmos. A ripple in the very math of the stars. The mathematics behind this are known as Einstein's field equations, which describe how matter and energy tell spacetime how to curve, and how that curvature then tells matter how to move. These equations are the foundation of modern astrophysics, providing the blueprint for how everything from the smallest moon to the largest supercluster behaves. They suggest a universe that is dynamic and responsive rather than static and rigid. The kind of science that carries the mind gently outward. General relativity also tells us that gravity isn't just about space, but also about the steady flow of time. The deeper you are in a gravitational well, where the curvature is strongest, the slower time actually moves compared to someone in a flatter region of space. This means that at the base of a mountain, time passes just a tiny bit differently than it does at the summit. A clock that breathes with the weight of the world. While Newtonian physics is still perfectly accurate for building bridges or launching satellites to the moon, it fails when things get incredibly heavy or incredibly fast. In those extremes, the simple idea of a pulling force breaks down, and we have to rely on the curves and dips of the spacetime fabric. It is a more complex way of looking at the world, but it reveals a universe that is far more interconnected than we ever imagined. A fabric that holds the distant and the near. In the vast emptiness between galaxies, spacetime is relatively flat and smooth, like a calm ocean at night. But as you move toward a star or a planet, the fabric begins to dip and slope, creating the celestial landscape that guides the movement of everything we see. We are all moving through these invisible valleys, guided by the weight of things we may never touch. The silent architecture of the night. This curvature even affects the signals we use for modern technology, like the global positioning system that helps us navigate our own world. The satellites in orbit are in a different part of Earth's gravitational curve than the receivers on the ground, so their internal clocks tick at a different rate. Without correcting for the curvature of spacetime, the coordinates on our maps would drift by several miles every single day. A bridge between the stars and our pockets. One of the most remarkable parts of this theory is that it was discovered entirely through thought and mathematics before it was ever seen in the physical world. It was a victory of human logic, realizing that the simplest explanation for why things fall was that the downward direction was actually a slope in the dimensions we inhabit. It changed gravity from a mystery of how much to a study of where. An invisible map drawn in the void. If we could see space-time, the universe would look like a stormy sea, with deep whirlpools around every star and massive swells around every galaxy. We are simply passengers on this textured surface, following the contours left behind by the birth and life of the cosmos. It is a world where distance and time are flexible, stretching and squeezing, depending on who is watching and how much mass is nearby. The steady rhythm of a bending world. The geometry of space reaches its most extreme expression in the heart of a black hole. When a massive star exhausts its nuclear fuel, its own gravity can cause a collapse so total that even the subatomic particles cannot hold back the inward pressure. This process creates a region of such high density that it essentially punches a hole in the structure of space-time itself. A point of no return. The boundary surrounding this region is known as the event horizon. It marks the precise distance from the center where the speed required to escape the gravitational pull exceeds the speed of light. Since nothing in the known universe can travel faster than light, any object or signal that crosses this invisible line is effectively removed from the observable universe. The ultimate physical boundary. Inside this horizon, the paths through space and time are warped to such a degree that every possible direction leads toward the center. This center is often referred to as the singularity, a point where the mass of many suns is compressed into a space of zero volume. According to the current mathematics of general relativity, the density and gravitational force at this point become infinite. A limit to our current understanding. While the concept of a black hole might seem like science fiction, their existence is a well-documented fact of modern astrophysics. They are not cosmic vacuum cleaners that actively suck things in from great distances, but rather massive objects that follow the same orbital laws as stars. If our sun were replaced by a black hole of equal mass, the Earth would continue in its orbit undisturbed, though the world would become much colder. A silent, dark anchor in the void. If a physical object were to fall toward a black hole, it would experience a process often called spaghettification. This is caused by tidal forces, which occur because gravity's strength changes rapidly over short distances. For someone falling feet first, the pull on their toes would be significantly stronger than the pull on their head. The stretching of physical form. In a small black hole, these tidal forces are so intense that they would pull an object apart long before it ever reached the event horizon. However, for supermassive black holes, the gradient is much shallower because the event horizon is so large. A traveler could theoretically cross the horizon of a giant black hole without feeling any immediate physical distress. A quiet transition into the unknown. These supermassive varieties are found at the centers of almost every large galaxy, including our own. Our local giant is named Sagittarius A*, a black hole with a mass roughly 4 million times that of the Sun. We know it exists because we have spent decades tracking the orbits of stars near the galactic center, watching them whip around an invisible point at millions of miles per hour. A heavy heart for the Milky Way. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A, showing a glowing ring of gas orbiting its dark center. This light comes from material being heated to millions of degrees as it rubs against itself while spiraling inward. The dark circle in the middle is not the black hole itself, but its shadow, the region where light is captured by the gravity of the event horizon. Evidence written in a ring of fire. The sheer scale of these objects helps define the structure of the universe on a grand level. Supermassive black holes appear to grow in tandem with their host galaxies, a relationship that scientists are still working to fully understand. They act as gravitational anchors, influencing the formation of stars and the distribution of gas across hundreds of thousands of light years. A balance between the small and the immense. For a smaller black hole, the event horizon might only be the size of a city, yet it holds the mass of several stars. This concentration of matter creates a gravitational field so steep that time itself slows down to a near standstill for any observer watching from the outside. To a distant viewer, an object falling toward the horizon would appear to slow down and fade away, never quite crossing the line. The kind of science that carries the mind gently outward. Despite their reputation for destruction, black holes may be essential to the life cycle of the cosmos. They recycle matter and energy, occasionally blasting jets of particles across intergalactic space at nearly the speed of light. These jets can prevent new stars from forming in some areas while triggering star birth in others by compressing distant clouds of gas. A cycle of cosmic transformation. There is a theoretical prediction made by Stephen Hawking that suggests black holes are not perfectly black. Through a quantum process, they may slowly emit radiation over incredibly long periods, eventually evaporating entirely. This process is called Hawking radiation, and it suggests that even the most permanent-seeming structures in the universe have a finite lifespan. A slow fade over trillions of years. The physics near a black hole is where our understanding of the very large and the very small begins to break down. This is the primary reason they are studied so intensely. They represent a natural laboratory where gravity and quantum mechanics must coexist. Solving the mystery of what happens at the singularity could lead to a theory of everything that unites all of physics. A doorway to a deeper logic. As we look out into the night, we are looking at a universe held together by these invisible giants. They are the extreme conclusion of gravity's relentless pull, reminding us that space is not just a void, but a material that can be folded, stretched, and even broken. Their presence is a fundamental part of the quiet, dark architecture that surrounds our world. The weight of the unseen universe. When two massive objects like black holes or neutron stars spiral toward each other, they don't just move through space. They actually churn the fabric of the universe itself, creating outward radiating ripples known as gravitational waves. These waves stretch and squeeze the very dimensions of length and time as they pass through everything in their path. A cosmic vibration. These ripples travel at the constant speed of light, carrying energy away from the most violent events in the cosmos. Because gravity interacts so weakly with matter, these waves can pass through solid planets, stars, and vast dust clouds without being scattered or absorbed. They arrive at our detectors as pure, unadulterated signals from the deep past. Information from the dark. The primary sources of these waves are binary systems where two dense remnants of dead stars orbit one another in a frantic dance. As they get closer, they move faster and faster, shedding gravitational energy into the void. This loss of energy causes their orbits to decay until they eventually collide and merge into a single, larger object. A final, silent crash. In the moment of merger, the power released in gravitational waves can briefly exceed the light output of every star in the observable universe combined. Yet, because these waves are distortions of space itself, they are incredibly difficult to pick up. By the time they reach us from a distant galaxy, the stretching they cause is smaller than the width of an atomic nucleus. Measuring the infinitesimal. To catch these signals, scientists use L-shaped observatories called interferometers, like those operated by the LIGO and Virgo collaborations. These facilities use high-powered lasers reflected between mirrors separated by several kilometers. If a gravitational wave passes through, it slightly changes the distance between the mirrors, a change the lasers can detect with impossible precision. A ruler made of light. As of early 2026, these detectors have transitioned from experimental tools into true astronomical observatories. They are now sensitive enough to pick up multiple events every month, cataloging a hidden population of black holes that were previously invisible to traditional telescopes. This work has revealed that black holes come in many more sizes than we once suspected. The unseen architecture of the void. One of the most significant breakthroughs occurred when detectors captured the merger of two neutron stars. Unlike black hole mergers, which are dark, this event also produced a massive burst of light and gamma rays. This multi-messenger event confirmed that such collisions are the primary source of heavy elements like gold and platinum in our universe. A forge in the stars. The gold in a wedding ring or the electronics in a phone likely originated from a gravitational wave event billions of years ago. When those neutron stars collided, they sprayed exotic, neutron-rich matter into space, where it decayed into the stable, heavy metals we find in the Earth's crust today. Our very history is tied to these ripples. A bridge between the elements. Before these discoveries, we could only see the universe through electromagnetic radiation like light, X-rays, and radio waves. Gravitational wave astronomy is more like hearing the universe. It provides a way to listen to the internal dynamics of objects that do not emit any light at all, giving us a completely new sense to explore the dark. A new way of sensing. The current network of detectors on Earth is being joined by even more sensitive instruments, some of which are planned for deployment in space. By placing detectors in orbit, scientists hope to catch much lower frequency waves. These waves come from even larger sources, such as the slow, majestic dance of supermassive black holes at the centers of distant galaxies, expanding the horizon. Wait until you hear about the invisible scaffolding that keeps those galaxies from flying apart. Beyond the collisions of stars, there is a background hum of gravitational waves filling the entire universe. This stochastic background is thought to be the overlapping noise of countless mergers happening simultaneously across billions of light years. It is a constant, low-frequency vibration that hints at the sheer activity of the hidden cosmos. A universal resonance. Einstein predicted these waves over a century ago using nothing but a chalkboard and his own intuition. He actually doubted we would ever be able to measure them because the effect on physical matter is so incredibly small. It took decades of engineering and the stabilization of lasers to prove that his mathematical theories were a literal description of reality. A century-old prophecy. When a wave passes through your body right now, you technically get a tiny bit taller and then a tiny bit thinner. The effect is far too small for any biological sense or even the most sensitive laboratory scale to notice. Yet, it happens every time a distant pair of stars ends their long spiral and becomes one. The quiet pulse of the distance. These observations have also allowed physicists to test the limits of general relativity in ways that were once impossible. By analyzing the chirp of the wave, the way it increases in frequency just before a merger, they can check if gravity behaves exactly as the equations suggest. So far, Einstein's work remains remarkably accurate, even in these extreme conditions. A test of the fundamental. This is built for bedtime listening. The precision required for LIGO and Virgo is so extreme that the mirrors must be shielded from the vibrations of distant ocean waves or nearby traffic. Even the quantum fluctuations of the laser light itself create noise that scientists must carefully filter out. It is a triumph of human engineering, turning the entire planet into a sensitive ear pressed against the walls of space. Listening to the stillness. Through these ripples, we have discovered that black holes often exist in pairs, suggesting that many large stars are born with a twin. These pairs live out their lives for billions of years before gravity finally pulls them together for their final act. Each detection is a record of a journey that began long before our solar system even existed. A message from the deep past. As the detectors continue to run through 2026 and beyond, the catalog of gravitational events is growing into a massive library of cosmic history. We are no longer limited to the light that manages to escape the dust and gas of space. We are now attuned to the very rhythm of the universe's most powerful movements. The heartbeat of the vacuum. The invisible grip of gravity does more than pull on matter. It actually stretches the very fabric of time itself, a phenomenon that sounds like science fiction but is a fundamental law of our universe. a silent slowing of the clock. General relativity teaches us that the stronger the gravitational pull, the slower time passes for an object within that field. This isn't just a mental trick or an error in how we build our watches. It is a physical reality where the seconds themselves expand. The weight of the seconds. Imagine two identical, perfectly synchronized atomic clocks placed at different altitudes on a massive planet. The clock sitting closer to the center of the planet's mass will fall behind the one positioned further away. A drift in the rhythm. Do you remember ever looking up at a high mountain peak and wondering how the air feels different up there? While the air is thinner, the passage of time is also technically faster for anyone standing on that summit compared to someone at the beach. The height of a moment. This difference is incredibly small, but it is measurable with our modern technology. A clock kept at sea level loses about a billionth of a second every day when compared to a clock kept at the top of a high mountain. A tiny, constant gap. These relaxing facts provide a window into the strange way our world is constructed. Even the core of our own planet is younger than its surface because of this gravitational time dilation. Scientific calculations suggest that the center of the Earth is roughly 2.5 years younger than the crust, simply because gravity is stronger deep inside. The youth of the core. This effect isn't limited to massive planets or stars. It affects the technology we use every single day. Global Positioning System satellites, or GPS, orbit high above the Earth, where the gravitational pull is significantly weaker than it is on the ground. A guide from the sky. Because they are further from Earth's mass, the clocks on these satellites tick faster than the clocks in our phones and cars. If engineers didn't account for this discrepancy, the entire navigation system would fail within hours, leading to errors of several kilometers. The necessity of precision. To fix this, the atomic clocks on board the satellites are programmed to run at a slightly different frequency before they are even launched. This ensures that when they reach orbit, their time matches up perfectly with the time we experience on the surface, aligning the two worlds. This is the kind of science that carries the mind gently outward. If you were to approach a truly massive object, like a neutron star, this warping of time would become much more dramatic. A few minutes spent near such an intense gravitational field could equate to years or decades passing for observers back on Earth. The stretching of a lifetime. Light also plays a role in how we perceive this slowing of time through a process called gravitational redshift. As light tries to climb out of a strong gravitational well, it loses energy, causing its frequency to shift toward the red end of the spectrum. A change in the glow. This shift is a direct signal that the source of the light is experiencing time at a different rate than the person observing it. Astronomers use this light-based evidence to confirm the presence of massive, invisible objects throughout the galaxy. The color of gravity. Even the sun causes a measurable delay in signals sent across the solar system. When we send radio waves past the sun to communicate with spacecraft, the sun's gravity curves space so much that the signals take a slightly longer path and arrive later than expected. A detour through the curves. In the 1970s, an experiment involved flying atomic clocks on commercial jetliners to test these theories at much lower speeds and altitudes. Even at 30,000 feet, the clocks showed the exact change predicted by Einstein's equations upon their return to the ground. Testing the invisible. The universe is not a rigid box where time flows at a steady, unchanging rate for everyone. Instead, it is a fluid environment where the presence of mass dictates how quickly or slowly the story of the cosmos unfolds. A variable pace. When we look at the stars, we are seeing objects that exist in their own distinct pockets of time. Some of those stars are so massive that the time passing on their surfaces is significantly decoupled from the time we measure here in our quiet corner of the galaxy. The isolation of the heavy. This relationship ensures that gravity and time are forever linked as two sides of the same coin. You cannot have the pull of a planet without the corresponding stretch of a second, creating a universe that is deeply interconnected at every level. The bond of the fundamental. The universe holds a secret that outweighs everything we can actually see. When astronomers look at distant galaxies, they notice something that shouldn't be possible according to the standard laws of physics. The stars at the very edges of these spinning spirals are moving much faster than they ought to. A speed that defies the light. If you imagine a merry-go-round, the people on the outer edge have to hold on tighter as the ride spins faster to avoid being thrown off. Gravity acts as that grip for a galaxy, keeping billions of stars tethered to the center. But when we calculate the mass of all the visible stars, gas, and dust, there simply isn't enough gravity to hold the system together at such high speeds. The missing tether. By all accounts, these galaxies should be flying apart, their outer stars drifting away into the void like sparks from a Catherine wheel. Yet they remain perfectly intact, held by an immense, invisible influence that provides the extra pull needed to maintain their structure. Science calls this unseen architect dark matter. The silent stabilizer. This substance does not emit, absorb, or reflect any form of light, making it entirely invisible to our most powerful telescopes. We only know it exists because we can see how its weight affects the visible world around it. It is like seeing the leaves of a tree move and knowing the wind is there, even though the air itself remains transparent. A presence felt, not seen. Studies of galactic rotation curves, which map the speed of stars at various distances from the center, consistently show a flat line where there should be a drop-off. Instead of slowing down as they get further from the dense core, stars in the outskirts maintain a high velocity. This suggests that the galaxy is sitting inside a massive, invisible halo of matter that extends far beyond the visible starlight. The weight of the void. This invisible influence is not just a local phenomenon confined to individual galaxies. When we look at massive clusters containing thousands of galaxies, we see them dancing around one another in ways that require far more mass than we can account for. The gravity of the visible matter is only a tiny fraction of what is actually holding these cosmic cities together. The glue of the clusters. Dark matter acts as a kind of invisible scaffolding for the entire universe. In the early stages of cosmic history, it likely clumped together first, creating gravitational wells that pulled in ordinary hydrogen and helium gas. This process allowed the first stars and galaxies to form, using the dark matter as a structural foundation. A cosmic blueprint. Without this hidden framework, the universe would look vastly different today. Large-scale structures like the Great Wall or the many filaments that make up the cosmic web might never have condensed. We inhabit a reality that was essentially built on the shoulders of something we cannot even touch. The foundation of the web. Despite its overwhelming presence, the exact nature of dark matter remains one of the greatest uncertainties in modern science. Many physicists suspect it consists of weakly interacting massive particles, or WIMPs, which would pass right through ordinary matter and even our own bodies without leaving a trace. Others look toward axions, hypothetical particles that are incredibly light and numerous. The search for a name. Because these particles have never been directly detected in a laboratory, their identity is still heavily contested. Some researchers even suggest that we might not need a new particle at least, but rather a modification to our understanding of gravity itself at very large scales. This remains a fringe view, as most evidence points toward a physical, though invisible, substance. The boundary of the knowns. Current experiments deep underground and in high-energy particle accelerators are trying to catch a single definitive glimpse of a dark matter interaction. Until that happens, we are in a period of scientific waiting, acknowledging the math and the observations while the fundamental what remains out of reach. It is a humble reminder that the vast majority of our universe is made of something we don't yet understand. A quiet mystery. This is built for bedtime listening, where the scale of the unknown can be a comfort rather than a frustration. Knowing that there is an invisible hand keeping the galaxies in their place allows us to see the night sky as a deeply ordered system. The stars we see are just the glowing foam on top of a much deeper, darker ocean of mass. The ocean beneath the light. In every corner of space, this invisible glue is working to counteract the expansion of the universe on a local level. It keeps our Milky Way bound to the Andromeda galaxy, ensuring that our local group of galaxies stays together even as the space between larger clusters grows wider. It is a force of cosmic togetherness. The pull of the hidden. Everything we have ever mapped, from the smallest asteroid to the largest sun, is effectively a passenger on a journey dictated by this dark matter. It is the dominant gravitational player in the cosmos, outweighing ordinary matter by a factor of about 5 to 1. We are the minority in a universe shaped by the invisible. A guest in the dark. This realization shifted our perspective from a universe made of things we can see to one where the visible is merely an exception. The glue of dark matter is what allows the clockwork of the heavens to function without breaking, providing the stability necessary for a predictable and enduring cosmos. The strength of the unseen. As we look toward the furthest reaches of space, we see the light of galaxies being bent and distorted by the gravity of dark matter that lies between them and us. This effect, known as gravitational lensing, allows us to map the distribution of this invisible mass as if we were looking through a cosmic magnifying glass. Mapping the shadows. It reveals a universe that is far more crowded than it appears. Every void between the stars is likely filled with this silent substance, exerting a steady and unwavering pull that keeps the celestial machinery in motion. It is a constant, quiet presence that supports everything we know. The silent partner of light. While dark matter acts as the invisible glue pulling the universe together, there is a counteracting force that works in the opposite direction. This mysterious influence, known as dark energy, exerts a repulsive pressure that pushes space itself apart. Unlike gravity, which grows weaker as objects move further away, dark energy appears to remain constant in its strength regardless of distance. The cosmic tug-of-war. For billions of years after the Big Bang, the density of matter was high enough that gravity was the dominant sculptor of the cosmos. During this era, the expansion of the universe was actually slowing down because the collective pull of all stars and gas acted like a brake. Around 5 or 6 billion years ago, as galaxies drifted further apart and matter became more diluted, dark energy began to take the lead. A shift in the celestial balance. Observations of distant Type Ia supernovae in the late 90s provided the first concrete evidence that the expansion of the universe is not slowing down, but accelerating. These stellar explosions serve as standard candles, allowing astronomers to measure exactly how fast the fabric of space is stretching. The data revealed that galaxies are receding from us at ever-increasing speeds, driven by this pervasive, repelling energy. The kind of science that carries the mind gently outward. Dark energy accounts for roughly 68% of the total energy density of the observable universe, making it the most influential factor in its long-term evolution. While gravity tries to pull local groups of galaxies into tight clusters, dark energy works to increase the void between these clusters. It is a constant competition between the desire for cosmic structure and the drive toward total dispersion. A struggle on a grand scale. The nature of this energy is often described by the cosmological constant, a term originally proposed by Albert Einstein in his field equations. Though he initially discarded the idea, modern measurements suggest that space possesses an inherent energy that does not thin out as the universe grows. This vacuum energy essentially provides a floor of repulsive force that never drops to zero. The persistence of the void. If dark energy continues to dominate the way current models suggest, the ultimate fate of the universe is a scenario called the heat death or the big freeze. In this future, galaxies will eventually move so far apart that their light will no longer be able to reach one another. The sky will gradually grow darker as the connections forged by gravity are severed by the relentless expansion of space. A long, cooling journey. The measurable redshift of light from the most distant objects in the cosmos acts as a speedometer for this expansion. As space stretches, the wavelengths of light traveling through it are pulled into longer, redder frequencies. By analyzing these shifts, researchers at institutions like the European Southern Observatory can track the history of the universe's growth with high precision. Reading the history of light. This expansion does not affect the objects themselves, but rather the space between them. Atoms, planets, and even solar systems are held together by forces much stronger than the push of dark energy, so they do not grow in size. It is only across the vast, empty gulfs between galactic superclusters that the repulsive effect becomes powerful enough to overcome the local grip of gravity. A stability within the stretch. There is another, more extreme theoretical possibility known as the Big Rip, where the strength of dark energy increases over time. If this were to happen, the repulsive force would eventually overcome the gravity holding galaxies together, then solar systems, and finally even the bonds holding atoms together. Current evidence from the Planck satellite suggests this is unlikely, pointing instead toward a steady, predictable expansion. The boundaries of the possible. The existence of dark energy implies that the universe is not a static container, but a dynamic and evolving entity. Every cubic centimeter of seemingly empty space contains a tiny amount of this energy, and as the universe expands, more space is created, resulting in more total dark energy. It is a self-reinforcing process that ensures the cosmos will continue to grow larger and colder indefinitely. Growth without end. Mapping the distribution of this energy requires looking back billions of years to see how the large-scale structure of the universe has changed. Projects like the Dark Energy Survey use massive cameras to catalog hundreds of millions of galaxies, looking for patterns in how they cluster. These patterns act as a fossil record, showing the moment when gravity lost its grip and dark energy took control of the cosmic expansion. Tracing the transition. We live in a unique epoch where both forces are clearly visible in the architecture of the heavens. We can still see the distant galaxies before they are pushed beyond our horizon, yet we can also feel the subtle acceleration that will one day hide them from view. It is a moment of clarity in a universe that is slowly, inevitably, moving toward a state of profound isolation. A window into the deep past. Even as the universe expands, the laws of physics remain the same, providing a sense of continuity across the eons. The same gravity that keeps a moon in orbit is the force that dark energy must overcome to tear the cosmic web apart. Understanding this balance helps us define the limits of our observable world and the eventual destination of every star we see. The final map of the heavens. The International Space Station provides a unique laboratory where the constant pull of Earth is countered by orbital velocity. This state of continuous freefall creates an environment of microgravity that profoundly alters human physiology. Without the downward tug of a planetary mass, the systems that evolved under a constant gravitational load begin to adapt in unexpected ways. A science for sleep. On Earth, gravity pulls the fluids in the body toward the lower extremities. In the microgravity of low Earth orbit, this gradient vanishes, causing blood and interstitial fluid to shift toward the upper body and head. This cephalad fluid shift results in a distinct facial puffiness and a decrease in leg volume, a phenomenon often described by aerospace medicine as bird leg syndrome.